Now we shall start our last final chapter, Fourier analysis. We shall start with some abstract discussion. Abstract Fourier theory. Firstly, we introduce the inner product space. Inner product space. Suppose X is a vector space, infinite dimensional, and we consider a map defined over the Cartesian product of X, which itself to the real numbers. This is called inner product. If it satisfies the following conditions. The first condition is that the inner product of any vector which itself is non-negative, and the inner product is 0 if and only if f is a 0 element. The second assumption is that symmetry. You can switch f and g, the result unchanged. The third is the linearly. Lambda f plus mu g, which the third element vector h, equal lambda f and h plus mu g and h. Here lambda and mu are real numbers, and f, g, h are elements in X, vectors in X. So if in an infinite dimensional vector space, you equip with a function using this symbol, equip with such a function having these three properties, then this function is called an inner product on the space X. And equipped with the inner product, this X is called the inner product space. Almost a Hilbert space. X is called inner product space. So this is very similar to our Euclidean space, but our Euclidean space is finite dimensional. Here we only interested in infinite dimensional space because our space will be function space, which are always infinite dimensional. So with the inner product, as in the study of Euclidean space, we can define the angle and the length of a vector. In particular, we can define the orthogonal. So for f and g in this space, we say that f is orthogonal with respect with g if the inner product of f and g is 0. So this is the concept of orthogonal. If f and g are orthogonal, then we have the following Pythagoras theorem: f plus or minus g square is precisely the norm of f squared plus g squared. The proof is quite easy. Firstly, we have not defined the norm because the inner product of f which itself is non-negative. So we can, since f is non-negative, we can define the norm of f to be the square root of this non-negative number. Okay, so this is the norm. Similar to the case in Euclidean space, you can consider this norm is the range of the vector. Okay, or if you put the starting point of the vector at the origin, and this norm is the distance from the endpoint to the origin. Okay, so this is the norm. Now, for orthogonal vectors f and g, the norm square of their multiplication or subtraction equals the sum of the square of their norm. The proof is quite easy. By the definition of norm, the for example, we prove the plus case. This is f plus g, f plus g. Expand this using the property of inner product. You will have f plus fg plus gf plus gg. Then this is f plus gg. Because f and g are orthogonal, so this term is 0, this term is also 0. Then this is precisely the norm square of f plus g. And this proves the Pythagoras theorem. Okay. So inner product make us possible to consider the space geometrically. Okay. So for the norm, we have introduced the norm using inner product. Here is the definition of norm. Norms has a similar property as in Euclidean space. So we list the basic property norm. So firstly is that norm is non-negative. Norm is 0 if and only if f is 0. And also f plus g will not greater than the norm of f, triangle inequality. Okay, and also scalar multiplication of norm is absolute value multiplying the norm of f. Very easy, similar to the Euclidean space. So this is the setting of our consideration. Now, having which inner product we can talk about orthogonal. Okay, now we consider a sequence of vectors in X. Let I from 1 to infinity be a sequence in X. If the inner product of Ej is delta Ij, that is, if I and j equal, they are 1. There is 1. If I and j not equal, the result is 0. So delta Ij is the usual Kronecker symbol. Okay. So if this sequence of vectors satisfies this condition, we say that they are orthonormal. An orthonormal system in X. Okay, and orthonormal systems always linearly independent. So it can be easy to see that in this case, Ei, any finite, many of them are linearly independent. I from 1 to n are linearly independent. Okay, this is easy to prove. For example, if you have lambda 1 E1 plus lambda m em 0, in making inner product which Ei, making inner product which Ei will give you Ei lambda 1 E1 plus lambda m em. This is 0. But using the orthogonal property, the inner product of Ei which E1 is 0, which E2 is also 0. The only non-zero term is which En. So this is lambda. This is Ei lambda I Ei. The other term vanishes, but this is precisely lambda I Ei. That is lambda I. So this proves that lambda I is 0. So all the lambda 1, lambda 2, lambda n are all 0. So this proves that E1, E2, Em are linearly independent. Okay. So this is a very important property. Then for a vector f in X, given n, we have a subspace denoted by xn to be spanned by this linearly independent vector e1, e2, en. This is an n-dimensional subspace of X. Subspace of X. Now, given F in the X, if F is in X, we can construct Fn to be the sum of the linear combination of E1, E2, En. We make an inner linear combination of E1, E2, En. But you need to determine the coefficient of the linear combination. The coefficient we take to be the inner product of F and En. Okay, we obtain this vector. This vector belongs to Xn. This is called projection, orthogonal projection of F on Xn on this subspace. Okay, so geometrically, this is Xn. Then a vector F, actually this is orthogonal. So this blue vector, this is our Fn. Okay, projection of F on Xn. It should be very easy. Maybe some of this you have studied in linear algebra. Okay. Now, the orthogonal projection has the minimal property. Minimal property. So we have this lemma, very important. Let EI be orthonormal. Normal means the length is 1. So the inner product of EI with EI is delta II. That is 1. Means that the norm of EI is 1. Okay, and for different I and j, the inner product is 0. Means that EI and EJ are orthogonal, orthonormal. Orthogonal and the unit is called orthonormal. Okay, so this is so suppose this is orthonormal system in X, and the F is a vector in X. Then we have this result. The norm of F minus Fn equal the infiniment of the distance from F to G. For every G in Xn, n is given. I should write n is a positive integer. Okay. So what's this mean? So this is Xn, and this is our F. This is our Fn. Then the left-hand side of our conclusion is the length of this vector. It's the length of this vector. Okay, this is F minus Fn. And for other G, if G is here, say G is here, then this distance is not less than the norm of F minus Fn. That is, Fn is the Fn is the element in Xn whose distance to F is the minimum. Every other G in Xn will have greater distance to F than Fn. Okay, than the projection Fn. Okay. So now we prove this result. Suppose G is an element in Xn, then G is the linear combination of the EI. Here the coefficient Xi are real numbers. Okay, then we consider this function denoted by phi from Rn to R. Because we have n xi, x1, x2, xn, we have n real numbers. These n real numbers determine the element G. So we can identify the G which this real number x1, x2, xn. This is a point in Rn. Therefore, we consider this function phi. Phi x is the f minus I from 1 xiei square. That is the distance from F to G square. Then this distance is the inner product of F minus xiei. F minus inner product xiei. And then you expand this inner product, you will obtain the norm of F square minus 2 I from 1 xi, the inner product of F which ei. Then plus, oh, I have no space to write. Okay. Then this is the norm of F square minus 2 I from 1 to n xi fei. Then plus I from 1 to n xi square. By a simple computation, expanding this inner product give you this result. Not difficult. So maybe I will do this. So to compute this inner product, here this is the inner product of F and F. Then subtract inner product of F with the sigma sum I from 1 to n xiei. Then subtract xiei with F. Then plus xiei with xiei itself. The middle two term give us the 2 here, the twice of the xi multiplying fei summing up here. The last term, using the orthogonal property of xiei, you should change the summation index in one of these sum, say by j. Then this can be written by xiei which the summation xj ej. Then using the orthogonal property, this summation only the term where j equal to I exists. When j equal to I, this is precisely xi. So that's xi square. Okay. This is an easy computation.